Imagine looking up at the night sky, filled with billions of stars, and realizing that despite the vastness of space, we have yet to find any signs of intelligent life. This is the Fermi Paradox, a question that haunts scientists and dreamers alike. Where is everyone? It's a paradox that shakes our understanding of the universe and forces us to confront the mysteries that lie beyond our reach. Space is not just a void, it's a realm of endless enigmas where the rules of physics twist and the boundaries of reality blur. Today, we're embarking on a journey to explore 50 of the most mind-bending space paradoxes, ideas that challenge everything we think we know about the cosmos. From the bizarre nature of black holes to the unsettling implications of time travel, these paradoxes will push your curiosity to its limits and leave you questioning the very fabric of existence. So, are you ready to dive into the unknown and uncover the secrets that space has been hiding? Let's begin. The Fermi Paradox is more than just a question, it's a puzzle that forces us to rethink our place in the universe. On one hand, the sheer scale of the cosmos suggests that life should be everywhere. With billions of stars in our galaxy alone and trillions of galaxies beyond, the odds of other civilizations existing seem overwhelming. Yet, despite decades of searching, we've found no evidence of intelligent life beyond Earth. This contradiction lies at the heart of the paradox, leaving us to wonder, are we truly alone, or is there something we're missing? Some scientists argue that advanced civilizations might be too far away for us to detect, while others suggest they could be hiding in plain sight, using technologies we can't yet comprehend. There's even the chilling possibility that intelligent life tends to self-destruct before it can make contact. Whatever the answer, the Fermi Paradox challenges us to confront the fragility of our existence and the vast unknowns of the cosmos. It's a humbling reminder that, in a universe so immense, we might still be the only ones asking these questions. Now, let's turn our attention to a paradox that's as simple as it is profound. Why is the night sky dark? At first glance, it might seem like a trivial question, but when you think about it, it's anything but. This is Olber's paradox, named after the 19th century astronomer Heinrich Olber, who pondered why, in an infinite universe filled with countless stars, the night sky isn't ablaze with light. If the universe were truly infinite and static, every line of sight should eventually land on a star, making the sky as bright as the surface of the sun. Yet here we are, gazing into a dark expanse. How can this be? The answer lies in the very fabric of our universe. First, the universe isn't static, it's expanding. This expansion stretches the light from distant stars, shifting it into wavelengths we can't see, like infrared or microwave. Second, the universe has a finite age, about 13.8 billion years. Light from stars beyond that distance hasn't had enough time to reach us. Together, these factors explain the darkness of the night sky, but they also reveal something deeper. The universe is dynamic, evolving, and far more complex than we once imagined. Olber's paradox isn't just about the darkness, it's a window into the origins and nature of the cosmos itself. Now, let's explore a paradox that bends the very fabric of time, the twin paradox. Imagine two identical twins, Alex and Jamie. Alex stays on Earth while Jamie boards a spacecraft and travels at near light speed to a distant star and back. When Jamie returns, something extraordinary happens. Jamie has aged less than Alex. This isn't science fiction. It's a real consequence of Einstein's theory of relativity. Time, as it turns out, isn't the fixed universal constant we once thought it was. Instead, it's relative, flowing differently depending on how fast you're moving and the strength of gravity you're experiencing. For Jamie, traveling at incredible speeds, time slows down compared to Alex's perspective on Earth. This effect, known as time dilation, has been confirmed by experiments with ultra-precise atomic clocks. But the twin paradox doesn't just challenge our intuition, it forces us to rethink the nature of time itself. Is time a river that flows at the same rate for everyone, or is it more like a winding path, bending and twisting depending on where you are and how you move? The twin paradox doesn't just answer questions, it raises new ones, inviting us to see the universe in a way that defies our everyday experience. Next, we come to a paradox that pits two of the greatest scientific theories against each other, the black hole information paradox. At its core, this paradox arises from a fundamental question: what happens to information when it falls into a black hole? According to Einstein's theory of general relativity, once something crosses the event horizon of a black hole, it's gone forever, irretrievably lost to the universe. But quantum mechanics tells a different story. It insists that information can never be destroyed, only transformed. So, which is it? Does information vanish, or is it somehow preserved? This question isn't just academic, it has profound implications for our understanding of reality. If information is truly lost, it would mean rewriting some of the most fundamental laws of physics. Scientists have proposed various solutions, from the idea that information is encoded in the radiation emitted by black holes, known as Hawking radiation, to the possibility that it's stored in a mysterious region called the holographic boundary. Yet, despite decades of research, the debate remains unsettled. The black hole information paradox isn't just a puzzle for physicists, it's a battleground where the rules of the universe itself are being tested. And as we grapple with it, we're reminded that even our most advanced theories are still works in progress, constantly evolving as we uncover the secrets of the cosmos. Now, let's step into a paradox that twists the very concept of cause and effect, the Bootstrap Paradox. Imagine you're a time traveler, and one day you meet an older version of yourself. They hand you a book you've never seen before, and tell you it's invaluable. Years later, when you're older, you travel back in time and give that same book to your younger self. But here's the catch: where did the book originally come from? It didn't appear out of thin air, yet it has no clear origin. This is the Bootstrap Paradox in action, a loop where an object or piece of information exists without a beginning, endlessly cycling through time. It's named after the phrase "pulling yourself up by your bootstraps," an impossible feat that mirrors the paradox's logic. This paradox doesn't just challenge our understanding of time travel, it forces us to rethink causality itself. If something can exist without a clear origin, does cause and effect even matter? The Bootstrap Paradox blurs the line between creation and existence, leaving us to wonder if some parts of reality might be self-sustaining loops, defying the very rules we thought governed the universe. It's a mind-bending thought experiment that doesn't just ask questions, it questions the foundation of how we perceive reality itself. Now, let's delve into one of the most famous paradoxes in the realm of time travel, the Grandfather Paradox. Picture this: you travel back in time and for whatever reason prevent your grandparents from meeting. If they never meet, your parent would never be born, and neither would you. But if you don't exist, how could you have traveled back in time to alter their meeting in the first place? It's a loop that seems impossible to untangle, challenging the very notion of cause and effect. This paradox isn't just a thought experiment, it's a fundamental problem that forces us to question the nature of time and possibility. So, how do we resolve it? One popular theory suggests that any changes you make in the past would create a parallel universe branching off from the original timeline. In this version of events, your grandparents might never meet in one reality, but you'd still exist in another. Another idea is the concept of a self-correcting timeline, where the universe somehow adjusts to prevent paradoxes, ensuring events unfold as they're meant to. These theories offer fascinating ways to reconcile the paradox, but they also raise new questions. Do parallel universes exist? Is the universe truly self-correcting, or are we simply unable to grasp the full mechanics of time? The Grandfather Paradox doesn't just challenge our understanding of time travel, it forces us to rethink the very fabric of reality, leaving us with more mysteries than answers. Next, we venture into one of the most provocative and mind-bending paradoxes of all, the simulation paradox. What if everything around us, the stars, the planets, even our own thoughts, is nothing more than an incredibly advanced simulation? This isn't just the plot of a sci-fi movie. It's a serious idea that some scientists and philosophers have explored. The core of the paradox lies in this question: if our universe is a simulation, how would we know? And if we are, does it even matter? On one hand, the sheer complexity of reality suggests it might be too intricate to be anything but real. Yet, on the other, the rapid advancement of technology raises the possibility that future civilizations could create simulations indistinguishable from reality. If that's true, statistically, there's a higher chance we're in one of those simulations rather than the original universe. But here's where it gets even stranger. If we are living in a simulation, what does that mean for free will? Are our choices truly ours, or are they pre-programmed? And if we ever discovered the truth, could we break free from the simulation, or would that knowledge itself be part of the code? The simulation paradox doesn't just challenge our understanding of reality, it forces us to confront the very nature of existence. It's a paradox that's as unsettling as it is fascinating, leaving us to wonder, if we are in a simulation, who's running it and why? Now, let's explore a paradox so strange it might make you question not just the universe but your own existence, the Boltzmann brain paradox. Named after the 19th century physicist Ludwig Boltzmann, this paradox starts with a startling idea: what if, in the vast emptiness of space, a self-aware brain could spontaneously form out of random fluctuations? It sounds like something out of a surrealist sci-fi story, but it's grounded in the laws of thermodynamics and probability. In an infinite universe, given enough time, even the most unlikely events are bound to happen. So, if a fully conscious brain could form randomly, why hasn't it? And if it has, how would we even know? This paradox isn't just a theoretical oddity. It challenges our understanding of consciousness and reality itself. If self-aware entities can emerge purely by chance, what does that say about the nature of our own minds? Are we the product of billions of years of evolution, or could we, too, be random fluctuations in the cosmos? Some scientists argue that the Boltzmann brain idea highlights the need for a deeper theory of the universe, one that explains why ordered structures like planets, stars, and life are more likely than random, isolated brains. Others see it as a profound reminder of how little we truly understand about the nature of existence. The Boltzmann brain paradox doesn't just question reality, it forces us to confront the unsettling possibility that everything we know could be nothing more than a fleeting accident in the void. Let's shift our focus to a paradox that's as elusive as it is essential, the dark matter paradox. Picture this: everything we can see, from the stars to the galaxies, makes up less than 5% of the universe. The rest, a mysterious substance called dark matter, which doesn't emit, absorb, or reflect light. We can't see it, touch it, or interact with it directly, yet its gravitational effects are undeniable. Galaxies rotate faster than they should, and the universe's structure wouldn't hold together without it. So, what exactly is dark matter? Scientists have been grappling with this question for decades, and the answers are anything but straightforward. One leading theory suggests that dark matter is made up of particles that don't interact with light or ordinary matter, except through gravity. These particles, known as WIMP, weakly interacting massive particles, could be everywhere, passing through us unnoticed. But despite countless experiments designed to detect them, we've come up empty-handed. Another intriguing idea is that dark matter isn't made of particles at all, but instead arises from modifications to the laws of gravity itself. Yet this theory, while creative, struggles to explain all the observed phenomena. The dark matter paradox isn't just a scientific challenge, it's a reminder of how much we still have to learn about the universe. It's a humbling thought. The vast majority of what exists is completely invisible to us, shaping the cosmos in ways we're only beginning to understand. Now, let's turn to a force that's even more mysterious than dark matter, dark energy. This enigmatic entity is the driving force behind one of the most baffling discoveries in modern cosmology, the accelerating expansion of the universe. In the late 1990s, astronomers studying distant supernova made a startling observation. The universe isn't just expanding, it's doing so at an ever-increasing rate. This shouldn't be possible. Based on our understanding of gravity, the expansion should be slowing down as the universe's contents pull on one another. Instead, something is pushing galaxies apart faster and faster. That something is what we call dark energy. But what exactly is it? The truth is we don't know. Dark energy is invisible, doesn't interact with matter, and seems to permeate all of space. One leading theory suggests it's a property of space itself, a constant energy density known as the cosmological constant. Another idea is that it's a dynamic field, like an anti-gravity force that changes over time. Whatever it is, dark energy makes up about 68% of the universe's total energy content, dwarfing even dark matter. Its existence challenges our understanding of physics on the deepest level, forcing us to rethink the fundamental forces that shape the cosmos. And perhaps most unsettling of all, dark energy could determine the ultimate fate of the universe. If it continues to dominate, the cosmos could end in a big freeze where galaxies are torn apart, stars fade, and the universe becomes a cold, empty void. The dark energy paradox doesn't just ask us to solve a mystery, it forces us to confront the fragility of existence itself, reminding us that the universe is far stranger and more wondrous than we ever imagined. The Pioneer Anomaly is one of those cosmic mysteries that make you scratch your head and wonder if we've got the universe all wrong. Back in the 1970s, NASA launched the Pioneer 10 and 11 spacecraft on missions to explore the outer solar system. These probes were marvels of engineering, designed to transmit data back to Earth as they ventured beyond Jupiter and Saturn. But as they journeyed farther into space, something unexpected happened. They began to slow down, slightly but consistently, in a way that couldn't be explained by known forces like gravity or solar radiation. This tiny deceleration, dubbed the Pioneer Anomaly, was so subtle it was barely noticeable, just a fraction of a nanometer per second squared, but it persisted, defying all explanations. For decades, scientists puzzled over what could be causing it. Some suggested it might be evidence of a new force, a shadowy fifth fundamental interaction that hadn't been accounted for. Others thought it could be due to the spacecraft themselves, perhaps heat radiating unevenly from their power systems. And then there were the more speculative ideas, like the possibility that dark matter or even modifications to Einstein's theory of gravity were at play. Eventually, after years of analysis, the mystery was largely resolved. It turned out to be caused by thermal radiation from the spacecraft's own power sources, pushing them ever so slightly off course. But the Pioneer Anomaly serves as a powerful reminder. Even in the cold vacuum of space, there are always surprises lurking, waiting to challenge our assumptions and expand our understanding of the cosmos. It's a testament to the fact that, no matter how much we think we know, the universe is always ready to throw us a curveball. Let's step back and consider a paradox that's as awe-inspiring as it is humbling, the size paradox. On one end of the spectrum, we have the universe itself, stretching over 93 billion light-years in diameter, filled with galaxies, stars, and planets so vast they defy comprehension. Yet, at the other extreme, we find the subatomic world, where particles like quarks and electrons are so small they're almost beyond our ability to measure. This staggering duality, the unimaginable vastness of the cosmos and the infinitesimal scale of its building blocks, forces us to confront a fundamental question. How can something so incomprehensibly large be made up of components so unbelievably tiny? It's a paradox that challenges our perception of reality and our place within it. We're caught in the middle, on a planet that's just the right size to support life, yet so insignificant in the grand scheme of the universe that it's easy to feel lost. But this paradox isn't just about size, it's about perspective. It invites us to marvel at the complexity of the cosmos, where the same laws of physics govern everything from the tiniest particles to the largest galaxies. It's a reminder that, whether we're gazing at the stars or peering through a microscope, we're part of a universe that's both infinitely vast and impossibly small, a duality that is as beautiful as it is bewildering. Here's a paradox that feels like it's straight out of a sci-fi novel, the Quantum-Zeno Paradox. In the quantum world, particles exist in a superposition of states, meaning they can be in multiple states at once until they're observed. But what if the act of observing a quantum system actually freezes it in place? That's the essence of the Quantum-Zeno Paradox, named after the ancient Greek philosopher Zeno of Elea, who famously argued that motion is an illusion. In quantum mechanics, if you continuously observe a particle, it won't change its state. It's as if the particle is saying, "I'll stay right here, thank you very much," while you're watching. This bizarre effect has been demonstrated in experiments where rapidly measuring an unstable atom prevents it from decaying. But what does this mean for our understanding of reality? Some interpretations suggest that observation itself plays a fundamental role in shaping the quantum world. Others argue that the paradox highlights the limitations of our measurement tools. Either way, it raises profound questions about the nature of existence. If simply watching something can prevent it from changing, how much of reality is shaped by our presence as observers? The Quantum-Zeno Paradox doesn't just challenge our understanding of quantum mechanics, it invites us to rethink the very nature of observation and its impact on the universe. It's a reminder that, in the quantum realm, the act of looking can change everything. Now, let's dive into a paradox that's as famous as it is bizarre: Schrödinger's cat. Imagine a cat placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the Geiger counter triggers the release of the poison, killing the cat. If it doesn't, the cat lives. But here's the twist: according to quantum mechanics, the atom exists in a superposition. It's both decayed and not decayed until it's observed. This means the cat, until the box is opened, is simultaneously alive and dead. It's a thought experiment designed to highlight the strangeness of quantum superposition, where particles can exist in multiple states at once. But Schrödinger's cat isn't just a quirky example, it's a profound challenge to our understanding of reality. If a cat, or anything else, can exist in such a bizarre state, what does that say about the nature of existence itself? One interpretation, the Copenhagen interpretation, suggests that the act of observation collapses the superposition, forcing the cat into a single state. Another theory, the many worlds interpretation, proposes that all possible outcomes happen, but in separate, branching universes. So, in one universe the cat lives and in another it dies. Regardless of which interpretation you lean toward, Schrödinger's cat forces us to confront the unsettling idea that reality might not be as fixed as we think. It's a paradox that doesn't just blur the line between life and death, it blurs the line between the possible and the impossible, leaving us to wonder what is real. The many worlds paradox takes the strangeness of quantum mechanics and amplifies it to an almost unimaginable scale. Imagine this: every time a quantum event occurs, like an electron choosing a path or a particle decaying, the universe splits into multiple versions, each representing a different outcome. In one reality, the electron goes left, in another, it goes right. This is the heart of the many worlds interpretation, a theory that suggests our universe is just one of countless parallel worlds, each branching endlessly from every possible quantum decision. At first glance, it sounds like the stuff of science fiction, but for many physicists, it's a serious contender for explaining the weird behavior of the quantum world. However, it also introduces a paradox. If every possible outcome exists in some parallel reality, does that mean our choices are meaningless? In a multiverse where every path is taken, is there still room for free will? Some argue yes, pointing out that even if all possibilities exist, we still experience only one of them, the one we're in. Others see it as a challenge to determinism, where the universe isn't governed by strict laws but is instead a chaotic web of infinite possibilities. The many worlds paradox doesn't just raise questions about the nature of reality. It forces us to confront the idea that every decision, no matter how small, could be creating entirely new universes. It's a theory that's as exhilarating as it is unsettling, reminding us that the cosmos might be far more complex and far stranger than we ever imagined. Let's tackle one of the most perplexing paradoxes in modern physics, the vacuum catastrophe. At first glance, the vacuum of space might seem like nothingness, a void devoid of matter or energy. But according to quantum field theory, empty space is anything but empty. It's teeming with virtual particles that pop in and out of existence, creating what's known as vacuum energy. This energy, while invisible, should have a measurable effect on the universe. Here's where the paradox comes in. When scientists calculate the expected value of this vacuum energy using quantum mechanics, they arrive at a number so astronomically large it would completely warp the fabric of the cosmos. Yet when they measure it, the observed value is staggeringly small, almost zero. This discrepancy, known as the vacuum catastrophe, is one of the biggest unsolved problems in physics. It's not just a mathematical headache, it challenges our understanding of the universe at its most fundamental level. Some theories suggest that our current models of quantum field theory are incomplete, missing a crucial piece of the puzzle. Others propose that there's a yet undiscovered mechanism that cancels out the vacuum energy, keeping it from overwhelming the universe, but the implications go even deeper. If the vacuum energy were just slightly different, the universe as we know it wouldn't exist. Stars wouldn't form, galaxies wouldn't coalesce, and life would never arise. The vacuum catastrophe isn't just a scientific anomaly, it's a reminder of how finely tuned and fragile our universe might be. It's a paradox that doesn't just ask us to solve a problem, it invites us to question the very nature of reality and our place within it. Now, let's explore a paradox that turns our understanding of emptiness on its head, the Unruh Effect. Imagine you're floating in space in what seems like a perfect vacuum, a void with no particles, no energy, just nothingness. Yet, if you suddenly accelerate, something extraordinary happens. From your perspective, that empty space isn't so empty anymore. It's filled with a warm glow of particles appearing out of nowhere. This phenomenon, predicted by physicist William Unruh in the 1970s, is one of the strangest consequences of quantum field theory. The Unruh effect tells us that what an observer perceives as a vacuum depends entirely on their motion. If you're at rest or moving at a constant speed, space looks empty, but accelerate and you'll detect particles, a kind of thermal bath created purely by your movement. It's as if the act of acceleration transforms nothingness into something. This paradox raises profound questions about the nature of reality. Are these particles real, or are they just an illusion created by the observer's motion? If two observers, one accelerating, one not, see different things, whose perspective is the true one? The Unruh effect challenges our intuition that reality is fixed and objective. Instead, it suggests that what we perceive depends on how we're moving through the universe. It's a reminder that even the simplest concepts, like emptiness, can become incredibly complex when viewed through the lens of physics. This paradox doesn't just deepen our understanding of quantum mechanics, it forces us to rethink the very nature of observation and existence itself. Now, let's venture into one of the most groundbreaking ideas in modern physics, Hawking radiation. Picture a black hole, a region of space so dense and powerful that not even light can escape its gravitational pull. For decades, black holes were thought to be eternal, swallowing everything that came too close without ever losing mass. But in the 1970s, Stephen Hawking turned this idea on its head. He proposed that black holes aren't entirely black, they emit radiation, slowly losing energy and mass over time until they eventually evaporate. This phenomenon, known as Hawking radiation, arises from the strange interplay between quantum mechanics and gravity. Near the event horizon of a black hole, pairs of particles and antiparticles pop into existence. Usually, these pairs annihilate each other almost instantly, but if one falls into the black hole while the other escapes, the black hole loses a tiny bit of mass. Over billions of years, this process can cause the black hole to shrink and disappear. But here's where things get paradoxical. If a black hole evaporates, what happens to all the information about the matter it once swallowed? According to quantum mechanics, information can't be destroyed. It must be preserved. Yet, Hawking radiation seems to suggest that information is lost forever, creating a fundamental conflict with the laws of physics. Some theories propose that the information is encoded in the radiation itself, while others suggest it's stored in a mysterious remnant left behind after the black hole evaporates. The Hawking radiation paradox doesn't just challenge our understanding of black holes. It forces us to reconcile the seemingly incompatible worlds of quantum mechanics and general relativity. It's a paradox that doesn't just ask questions, it pushes the boundaries of our knowledge, inviting us to rethink the very fabric of the universe. Now, let's dive into one of the most mind-boggling paradoxes in quantum physics, quantum entanglement. Imagine two particles born together and then separated by vast distances even across the universe. No matter how far apart they are, they remain mysteriously connected. Change the state of one particle and the other instantly responds, as if they're sharing a secret language faster than the speed of light. This phenomenon, famously called spooky action at a distance by Einstein, defies everything we know about classical physics. It's not just a quirk of quantum mechanics, it's a fundamental challenge to our understanding of reality. How can two particles communicate instantaneously without any physical link? The implications are staggering. For one, it suggests that the universe operates on a level of interconnectedness that transcends space and time. If particles can influence each other across vast distances, what does that mean for causality, the idea that cause must precede effect? Some interpretations argue that the particles don't actually communicate but instead share a deeper, underlying reality that's hidden from us. Others propose that entanglement reveals the existence of a universal fabric that binds everything together. But the paradox doesn't stop there. If we can harness entanglement, it could revolutionize communication, creating unhackable quantum networks that transmit information instantly. Yet, this raises ethical questions. Should we meddle with such fundamental forces of nature? Quantum entanglement isn't just a scientific curiosity. It's a window into the profound and often unsettling mysteries of the cosmos. It challenges us to rethink what we know about connection, causality, and the very nature of existence itself. Now, let's explore the EPR paradox, a thought experiment that shook the foundations of quantum mechanics and sparked one of the greatest scientific debates of the 20th century. In 1935, Albert Einstein, along with physicists Boris Podolsky and Nathan Rosen, proposed a scenario to challenge the idea that quantum mechanics provided a complete description of reality. Here's how it works. Imagine two particles created together and then separated by vast distances. According to quantum mechanics, measuring one particle instantly determines the state of the other, no matter how far apart they are. Einstein argued that this spooky action at a distance violated the principle of locality, the idea that an object is only directly influenced by its immediate surroundings. He believed this paradox revealed a flaw in quantum mechanics, suggesting that there must be hidden variables, unknown factors, that determine the particle's properties before they're measured. But was Einstein right? Decades later, experiments like those based on John Bell's work showed that quantum entanglement behaves exactly as quantum mechanics predicts, without the need for hidden variables. This doesn't just validate quantum mechanics, it forces us to rethink the nature of reality itself. If particles can instantaneously communicate across vast distances, does that mean the universe operates on a deeper level of interconnectedness than we can perceive? The EPR paradox doesn't just challenge the completeness of quantum mechanics, it invites us to confront the possibility that reality is far stranger and more intertwined than we ever imagined. It's a reminder that even our greatest minds can be humbled by the mysteries of the cosmos. Now, let's turn our attention to a paradox that could rewrite our understanding of black holes, the Firewall Paradox. Imagine approaching the event horizon of a black hole, the point of no return where gravity is so strong that not even light can escape. According to classical physics, crossing this boundary would be uneventful. You'd simply drift deeper into the black hole's clutches. But quantum mechanics paints a far more dramatic picture. Theoretical physicists have proposed that a blazing firewall of high-energy particles might exist at the event horizon, incinerating anything that comes too close. This idea stems from attempts to reconcile two fundamental principles, the conservation of information and the no-drama principle of black holes. The conservation of information insists that information about matter falling into a black hole must be preserved even if it's scrambled beyond recognition. However, if this information is encoded in the radiation escaping the black hole, a process known as Hawking radiation, it could create a paradox at the event horizon. Why? Because the entanglement between particles inside and outside the black hole would have to break, releasing an enormous amount of energy in the form of a firewall. But here's the catch: if firewalls exist, they violate Einstein's theory of general relativity, which predicts that crossing the event horizon should be uneventful. This paradox has divided physicists, with some arguing that firewalls are a necessary consequence of quantum mechanics, while others seek alternative solutions to preserve the smoothness of the event horizon. The Firewall Paradox doesn't just challenge our understanding of black holes, it forces us to confront the limits of our current theories and the possibility that we're missing a crucial piece of the puzzle. It's a reminder that even the most well-established ideas can be upended by the mysteries of the cosmos. Now, let's explore one of the most fascinating and speculative concepts in astrophysics, the white hole paradox. While black holes are notorious for their ability to swallow everything that crosses their event horizon, white holes are their hypothetical opposites, regions of space where matter and energy are expelled rather than absorbed. Imagine a cosmic fountain endlessly spewing material into the universe, but here's the twist: nothing can enter a white hole, just as nothing can escape a black hole. This idea isn't just a thought experiment. It emerges from the mathematical equations of general relativity, suggesting that white holes could exist as a kind of mirror image of black holes. But if they do, why haven't we observed one? Some theories propose that white holes could be the remnants of black holes that have evaporated via Hawking radiation, essentially rebounding into a new state. Others suggest they might be connected to black holes via wormholes, forming a bridge between 2 points in space-time. However, these ideas come with their own set of paradoxes. For instance, if white holes expel matter, where does that matter come from? Is it conserved, or does it violate the laws of physics? And if they're linked to black holes, how does information flow between them? The white hole paradox doesn't just challenge our understanding of cosmic phenomena. It forces us to grapple with the limits of our theories and the possibility of entirely new kinds of physics. It's a reminder that the universe is full of mysteries waiting to be unraveled, and that even the wildest ideas can lead to groundbreaking discoveries. Whether white holes are real or just a mathematical curiosity, they invite us to push the boundaries of what we know and imagine the unimaginable. The Big Bang Singularity Paradox takes us to the very beginning of everything, the moment the universe burst into existence. According to the leading theory, the universe started as an infinitesimally small, infinitely dense point called a singularity. But here's the problem. Our current understanding of physics breaks down when we try to describe it. General relativity, which governs the large-scale structure of the cosmos, predicts that a singularity must have existed at the start of the Big Bang. Yet, this concept clashes with quantum mechanics, which rules the behavior of the very small. In the quantum world, infinities don't exist, everything is finite and quantized. So how can the universe have begun as a singularity where density and temperature are infinite? This paradox forces us to confront the limits of our knowledge. Was the Big Bang truly a singularity, or is our understanding incomplete? Some theories suggest that the singularity might be a placeholder for a deeper reality, something quantum gravity or string theory could explain. Others propose that time itself might have a different nature at the very beginning, making the concept of a singularity irrelevant. This paradox doesn't just challenge our understanding of the universe's origin, it invites us to rethink the nature of time, space, and existence itself. It's a reminder that the birth of the cosmos is still one of the greatest mysteries waiting to be unraveled. Now, let's step into one of the most speculative and mind-expanding ideas in modern science, the Multiverse Paradox. Imagine a reality where our universe isn't the only one, where an infinite number of universes exist, each with its own unique set of physical laws, constants, and even versions of ourselves. This isn't just science fiction. It's a serious hypothesis supported by theories like cosmic inflation, string theory, and quantum mechanics. But here's where things get paradoxical. If there are infinite universes, does that mean every possible scenario exists somewhere? Is there a version of you who's a rock star, a scientist, or even a completely different species? While the idea is tantalizing, it also raises profound questions about the nature of reality. For one, if every possible outcome exists in some universe, does that make our choices here less meaningful? Some argue that the multiverse theory gives us a cosmic perspective, showing that our existence is just one thread in an infinite tapestry. Others worry it could diminish our sense of uniqueness, reducing our lives to a statistical inevitability rather than a singular act of chance. But the paradox doesn't stop there. If the multiverse is real, how could we ever prove it? Evidence for other universes might be forever out of reach, trapped beyond the boundaries of our observable cosmos. This paradox challenges us to confront the limits of human knowledge and the possibility that reality is far more complex than we can imagine. It's a reminder that, even in a universe as vast as ours, there may be whole new realms of existence waiting to be discovered, or at least pondered. Next, let's explore a paradox that's so fundamental to our daily lives we often take it for granted, the arrow of time. Think about it. Why does time always move forward? We can remember the past, but not the future. Eggs can shatter, but they never unshatter. This one-way flow of time is so ingrained in our experience that it's hard to imagine it any other way. Yet, here's the paradox. The laws of physics don't inherently distinguish between past and future. At the microscopic level, most physical processes are reversible. So, why does time have a direction at all? This is the arrow of time paradox, and it's one of the deepest mysteries in science. One key to solving it lies in entropy, a measure of disorder in a system. The second law of thermodynamics tells us that entropy always increases over time, creating a natural directionality. For example, a drop of ink spreads out in water, increasing entropy, but it never spontaneously gathers back into a drop. This gives time its arrow, but entropy isn't the whole story. Some theories suggest that the Big Bang played a crucial role. If the universe began in a highly ordered state, a low entropy condition, then time's direction might be a consequence of that initial state. Others propose that the arrow of time is tied to the expansion of the universe, with each moment stretching space and creating a sense of forward motion. Still, these ideas raise new questions. Could there be regions of the universe where time flows backward? Or is time's direction universal, an unbreakable rule that governs everything from the smallest particles to the largest galaxies? The arrow of time paradox doesn't just challenge our understanding of physics, it forces us to confront the nature of existence itself. It's a reminder that even the most familiar aspects of reality can hide profound mysteries waiting to be uncovered. Now, let's step into a paradox that bends the rules of time and identity, the time traveler's immunity paradox. Imagine you're a time traveler who jumps back to the past. While there, you make a change, perhaps you prevent an event that was supposed to happen. But here's the twist: no matter what you do, the timeline around you adjusts and you remain unaffected by your own actions. You're somehow immune to the changes you create. This idea challenges our understanding of causality, the principle that every effect must have a cause. Normally, altering the past would ripple through time, potentially changing the future and even erasing your own existence. But if you're immune, it raises a startling question. Does your presence in the past create a parallel timeline, or are you somehow outside the normal flow of cause and effect? Some theories suggest that the act of time travel itself could create a protective bubble around the traveler, shielding them from the consequences of their actions. Others argue that this immunity might hint at a deeper truth, that free will is an illusion and our actions are predetermined even in the past. But what does this mean for the nature of reality? If a time traveler can change the past without altering their own future, does that mean the past is more malleable than we thought? Or does it imply that time is a fixed tapestry where every thread is already woven and our journey through it is just an illusion? The time traveler's immunity paradox doesn't just question the mechanics of time travel. It forces us to confront the very essence of free will, causality, and our place in the grand scheme of the universe. It's a reminder that time, like the cosmos itself, is full of mysteries waiting to be unraveled. Let's take a journey into one of the most thought-provoking paradoxes of quantum mechanics, the quantum immortality paradox. Imagine you're faced with a life or death scenario, say, a game of Russian roulette. In most realities, the outcome is grim, but what if in one universe you survive? The quantum immortality paradox suggests that consciousness might not end with death. Instead, it could persist in parallel realities where you continue to exist. This idea stems from the many worlds interpretation, which posits that every possible outcome of a quantum event creates a branching universe. From your perspective, it might seem like you've defied death, but in reality, you're simply experiencing the universe where the outcome is favorable. But what does this mean for the nature of life and death? On one hand, it offers a surreal form of comfort, the idea that consciousness might never truly end. On the other, it raises unsettling questions. If consciousness persists across infinite universes, does that make death an illusion? Or is it simply a transition to another version of reality? Some argue that this paradox challenges our understanding of identity. Are we the same person in every universe, or does each version of us diverge into a unique existence? Others see it as a profound reminder of the interconnectedness of all possibilities, suggesting that life might be far more resilient than we think. The quantum immortality paradox doesn't just push the boundaries of quantum mechanics, it forces us to confront the deepest questions about existence, mortality, and the nature of reality itself. It's a reminder that the universe is full of mysteries that defy our everyday experience, inviting us to imagine the unimaginable. At the heart of quantum mechanics lies a paradox that blurs the line between observer and observed, the observer effect. It's a phenomenon so strange it almost feels like science fiction. Simply by watching a quantum system, we can change its behavior. Take the classic double-slit experiment, for example. When particles like electrons are fired through two slits, they create an interference pattern behaving like waves. But the moment you place a detector to observe which slit the electron passes through, the interference pattern disappears. The electrons suddenly act like particles, not waves. It's as if the act of observation itself forces the system to choose a state. This effect isn't just a quirk of the experiment, it's a fundamental principle of quantum mechanics, suggesting that the observer plays a critical role in shaping reality. But what does this mean for the nature of existence? Some interpretations argue that consciousness itself is the key, proposing that without an observer, the universe remains in a state of infinite possibilities. Others take a more pragmatic view, suggesting that the act of measurement inevitably disturbs the system, creating the observed outcome. This paradox doesn't just challenge our understanding of the quantum world, it forces us to confront our place within it. Are we passive witnesses to the universe or active participants in its unfolding? The observer effect invites us to rethink the relationship between mind and matter, raising profound questions about the nature of reality itself. It's a reminder that, in the quantum realm, even the act of looking can change everything. Now, let's turn our gaze toward one of the most profound and unsettling predictions in cosmology, the heat-death paradox. Picture the universe billions of years from now, a vast, cold, and empty expanse where all stars have burned out, black holes have evaporated, and even the last remnants of energy have been reduced to a faint, uniform glow. This is heat death, the ultimate fate of the cosmos according to the second law of thermodynamics. As entropy increases, the universe reaches a state of maximum disorder, where no energy is left to sustain motion, life, or even change. But here's the paradox: if the universe ends in heat death, does time itself cease to have meaning? Without events or processes to mark its passage, how can time continue to flow? It's a question that forces us to confront the limits of our understanding. Some theories suggest that time might become irrelevant in such a state, a frozen backdrop to an unchanging universe. Others propose that heat death isn't the end but a new beginning, a prelude to a future where quantum fluctuations could spark a new Big Bang, creating a cycle of universes. But the implications go even deeper. If entropy dictates the fate of the cosmos, what does that mean for our existence? Are we just fleeting sparks in a universe destined for stillness, or is there a deeper purpose to the chaos we see around us? The heat-death paradox doesn't just challenge our understanding of the universe's end. It forces us to rethink the nature of time, existence, and our place within the grand tapestry of reality. It's a reminder that even in the face of ultimate entropy, the cosmos still holds mysteries waiting to be explored. Now, let's venture into a paradox that stretches the imagination to its absolute limits, the infinite universe paradox. Imagine a universe that's not just vast but truly infinite, a cosmos with no boundaries, no edges, and no end. In such a universe, every possible configuration of matter and energy must exist somewhere. That means somewhere out there, there's a planet identical to Earth with a version of you reading these exact words. In fact, there could be an infinite number of them, each slightly different from the choices you've made to the paths you've taken. This paradox isn't just a mind-bending thought experiment, it's a consequence of infinity itself. If the universe is infinite, every possible event, no matter how unlikely, must occur not just once but an infinite number of times. But here's where it gets even stranger. If infinite copies of us exist, does that mean our choices are meaningful, or are they just one of countless possibilities playing out across the cosmos? Some argue that infinity diminishes our uniqueness, reducing our lives to statistical inevitabilities. Others see it as a profound reminder of the interconnectedness of all things, suggesting that every decision ripples through an infinite tapestry of realities. This paradox doesn't just challenge our understanding of the universe, It forces us to confront the nature of identity, free will, and existence itself. Are we singular beings or just one thread in an endless cosmic weave? The Infinite Universe Paradox invites us to explore the boundaries of what's possible, reminding us that even in a universe without limits, the questions we ask are just as infinite as the answers we seek. Now, let's dive into one of the most perplexing issues in modern cosmology, the cosmological constant problem. At the core of this paradox lies a number that shouldn't be this controversial, a value that represents the energy density of empty space, also known as dark energy. When physicists first tried to calculate this number using quantum field theory, they arrived at a result that's off by a mind-boggling factor of 10 to the 120th power. That's a 1 followed by 120 zeros, a discrepancy so enormous it's been called the worst prediction in the history of science. But why is this such a big deal? Well, the cosmological constant is crucial because it's the force driving the accelerated expansion of the universe. If its value were even slightly larger, galaxies wouldn't have formed, and life as we know it would be impossible. If it were smaller, the universe might have collapsed back in on itself long ago. So, the fact that it's so finely tuned for our existence raises profound questions. Is this just a cosmic coincidence, or is there something deeper at play? Some theories suggest that the cosmological constant might be the result of a yet undiscovered law of physics, one that reconciles quantum mechanics and general relativity. Others propose that we're simply missing a key piece of the puzzle, like an unknown symmetry or an overlooked interaction. And then there's the possibility of a multiverse, where an infinite number of universes exist, each with its own cosmological constant, and we just happen to live in the one where it's perfectly balanced. This paradox isn't just a mathematical headache, it's a window into the fundamental nature of the universe. It forces us to confront the possibility that our understanding of physics is incomplete, and that reality might be far stranger and more intricate than we've ever imagined. Now, let's shift our focus to a particle so elusive it's often called the ghost of the universe, the neutrino. These tiny particles are everywhere. Trillions pass through your body every second, but they're so weakly interactive that they rarely leave a trace. For decades, scientists believed neutrinos were massless, just like photons. But then came a discovery that turned everything upside down. Neutrinos oscillate. This means they can change their flavor, switching between three types: electron, muon, and tau neutrinos as they travel through space. This oscillation implies that neutrinos must have mass, however tiny. But here's the paradox: the standard model of particle physics, our most accurate theory of the universe's building blocks, doesn't account for neutrino mass. So, if neutrinos oscillate, what does that mean for our understanding of matter? Some theories suggest that neutrinos could be a window into new physics, hinting at particles and forces beyond the standard model. Others propose that neutrinos might have a unique mechanism for acquiring mass, possibly linked to dark matter or even higher dimensions. The implications are staggering. If neutrinos have mass, they could be the key to explaining why the universe is filled with matter instead of antimatter. It's a mystery that touches on the very origins of existence. The neutrino paradox doesn't just challenge the standard model. It invites us to explore the hidden layers of reality, reminding us that even the most elusive particles can hold the secrets to the cosmos. Now, let's unravel one of the most persistent mysteries in astrophysics, the missing Baryon paradox. Baryons, particles like protons and neutrons, are the building blocks of the visible universe. Everything from stars and planets to the atoms in your body is made of them. But here's the catch: when scientists tally up all the baryons predicted by the Big Bang, they find that about half of them are missing. It's like trying to balance a cosmic checkbook and coming up short. So, where could these baryons have gone? One leading theory suggests they're hiding in the vast, invisible webs of warm, hot intergalactic medium, or WIM. This is a diffuse network of gas filaments that stretches between galaxies, too faint to detect with traditional telescopes. Another possibility is that baryons have been ejected from galaxies by supermassive black holes or supernova explosions, scattering them into the intergalactic void where they're incredibly hard to spot. But why does this matter? These missing baryons aren't just a scientific curiosity. They're crucial for understanding the structure and history of the universe. If they're hiding in the WIM, for example, it could reveal how galaxies form and evolve over time. And if they've been expelled into deep space, it might tell us something profound about the forces shaping the cosmos. Recent advances in technology, like X-ray telescopes and radio surveys, are beginning to shed light on this mystery, offering tantalizing clues about where these elusive particles might be. The missing baryon paradox doesn't just highlight the gaps in our knowledge, it invites us to explore the hidden corners of the universe, reminding us that even the most fundamental questions can lead to groundbreaking discoveries. It's a mystery that proves the cosmos is still full of surprises waiting to be uncovered. Now, let's tackle one of the universe's most puzzling quirks, the horizon problem. Imagine looking at the night sky in opposite directions, say, one star to the east and another to the west. These two stars are so far apart that light from one hasn't had time to reach the other since the Big Bang. Yet somehow they're at nearly the same temperature and exhibit remarkably similar properties. How can regions so distant from each other be so uniform? This is the horizon problem, a paradox that challenges our understanding of the early universe. According to classical physics, there hasn't been enough time since the Big Bang for these regions to interact and reach equilibrium. So how did they end up so alike? One of the most compelling explanations is cosmic inflation, a theory proposing that the universe underwent an exponential expansion just fractions of a second after the Big Bang. During this rapid growth, regions that were once close together were stretched far apart, smoothing out irregularities and creating the uniformity we observe today. But inflation isn't the only idea on the table. Some theories suggest that the universe might have been initially connected in ways we don't yet understand, while others propose that the laws of physics themselves could have acted differently in the early cosmos. The horizon problem isn't just a cosmic puzzle, it's a window into the universe's infancy, pushing us to rethink how it began and evolved. It's a reminder that even the most fundamental aspects of reality can hide profound mysteries waiting to be uncovered. Let's take a step into one of the universe's most head-scratching mysteries, the flatness problem. Picture the shape of the cosmos, vast, expansive, and seemingly flat. But why is that surprising? Well, according to Einstein's theory of general relativity, the universe's geometry is determined by its density. Too much matter and space curves inward like a sphere. Too little and it curves outward like a saddle. A just right amount, however, makes the universe flat. Here's the catch: for the universe to be as flat as we observe today, its density at the time of the Big Bang had to be incredibly precise, so finely tuned that even the tiniest deviation would have led to a vastly different cosmos. It's like balancing a pencil on its tip for billions of years. How did the universe pull this off? One leading explanation is cosmic inflation, a rapid expansion in the early universe that smoothed out any curvature, making space appear flat on large scales. But inflation isn't the only idea. Some theories suggest that the universe's flatness might be a clue to deeper physics, like extra dimensions or a multiverse where our universe is just one of many. This paradox doesn't just challenge our understanding of the Big Bang. It forces us to confront the possibility that the cosmos is far more intricate and finely balanced than we ever imagined. It's a reminder that even the simplest observations can lead to profound questions about the nature of reality itself, inviting us to explore the universe with fresh eyes and boundless curiosity. Now, let's dive into a paradox that's been puzzling physicists for decades, the magnetic monopole paradox. Magnets, as we know them, always come with two poles, a north and a south. Break a magnet in half and you'll still end up with two poles on each piece. But what if we told you that theory predicts the existence of magnetic monopoles particles with just one pole, either north or south? These hypothetical entities aren't just a curious idea. They emerge naturally from grand unified theories which attempt to merge the fundamental forces of nature. If monopoles exist, they could explain a lot about the structure of the universe, from the nature of magnetism to the origins of cosmic inflation. Yet, despite decades of searching, no one has ever observed a magnetic monopole. So, where are they? This paradox isn't just about missing particles. It's a profound challenge to our understanding of physics. One possibility is that monopoles were created in the early universe but have since decayed or become so rare that they're nearly impossible to detect. Another idea is that they're hidden in regions of space we can't yet explore, like the hearts of black holes or the voids between galaxies. Some theories even suggest that monopoles could be evidence of extra dimensions or new symmetries in the laws of physics. The magnetic monopole paradox doesn't just question the nature of magnetism. It forces us to confront the gaps in our understanding of the universe. It's a reminder that, even in the most familiar phenomena, there are mysteries waiting to be uncovered, pushing us to think beyond the boundaries of what we know. Now, let's explore a paradox that feels like it's straight out of a time travel thriller. The Tachyonic Antitelephone Paradox. Imagine a particle that moves faster than light, a tachyon. While we've never observed one, tachyons are a fascinating theoretical concept, raising the possibility of sending messages backward in time. Here's how it would work. If you could harness tachyons to transmit information, the message would arrive at its destination before it was sent, effectively allowing communication with the past. Sounds like science fiction, right? But the implications are anything but simple. If tachyons exist and can be used to send messages, they'd turn our understanding of causality, the idea that cause always precedes effect, on its head. Picture this: you send a message to your past self warning of an impending disaster. Your past self then avoids that disaster, meaning the message was never sent in the first place. It's a classic time loop paradox where cause and effect become entangled in an endless cycle. Some theories suggest that such paradoxes might be prevented by the laws of physics, which could prevent tachyons from carrying meaningful information. Others propose that the universe might split into parallel timelines to avoid contradictions, with each decision creating a new reality. The Tachyonic Antitelephone Paradox doesn't just challenge our understanding of communication, it forces us to confront the very nature of time and causality. It's a reminder that even the most speculative ideas can push the boundaries of what we thought was possible, inviting us to explore the universe's deepest mysteries with curiosity and wonder. Now, let's turn our attention to one of the most tantalizing ideas in space exploration, the Alcubierre Drive. Proposed by physicist Miguel Alcubierre in 1994, this concept suggests a way to travel faster than light without breaking the laws of physics, at least not directly. Here's how it works. Instead of moving through space, the Alcubierre Drive would warp space itself, creating a warp bubble that contracts space in front of the spacecraft and expands it behind. This would allow the ship to effectively ride a wave of spacetime, reaching distant stars in a fraction of the time it would take using conventional propulsion. It's a concept straight out of science fiction, but it's grounded in the mathematics of Einstein's general relativity. However, here's where the paradox comes in. To create such a warp bubble, you'd need an enormous amount of negative energy, something we've never observed in nature. And even if we could generate it, the drive raises questions about causality. If you could travel faster than light, could you send messages or even yourself back in time? This paradox doesn't just challenge our understanding of space travel, it forces us to confront the fundamental limits of physics. Some theories suggest that exotic matter or quantum effects might make the Alcubierre Drive possible, while others argue that it's inherently unfeasible, a mathematical curiosity with no practical applications. What's clear is that the Alcubierre Drive pushes the boundaries of our knowledge, inviting us to imagine a future where the stars are no longer out of reach. It's a reminder that even the wildest ideas can inspire us to rethink what's possible, sparking the curiosity and innovation that drive humanity forward. Next, let's delve into a concept that's as ambitious as it is fascinating: the Dyson Sphere. Imagine a civilization so advanced that it constructs a massive structure, or even a swarm of structures around a star to capture its energy. The idea, first proposed by physicist Freeman Dyson, envisions a level of technological mastery that could power entire galaxies. Such a structure would harness unimaginable amounts of energy, transforming a star's output into usable power for interstellar civilizations. Yet, here's the paradox: if Dyson spheres exist, why haven't we found any evidence of them? One possibility is that these megastructures are simply beyond our current ability to detect. They might emit energy in ways we're not yet equipped to observe, or they could be camouflaged to avoid detection by other advanced civilizations. Another intriguing theory is that Dyson spheres might not look like the solid, shell-like structures we often imagine. Instead, they could be vast networks of energy-collecting satellites, known as Dyson swarms, making them harder to spot. On the other hand, some scientists argue that such megastructures might not exist at all, or that civilizations capable of building them might have evolved beyond the need for such energy-harvesting methods. This paradox doesn't just challenge our search for extraterrestrial intelligence, it forces us to rethink the trajectory of technological progress. Are Dyson spheres the pinnacle of a civilization's development, or are they merely a stepping stone to even greater achievements? While we may not have answers yet, the very idea of such structures inspires us to think bigger, to imagine what might be possible when humanity, or another civilization, reaches for the stars. It's a reminder that the universe is full of possibilities, waiting for us to uncover them, one discovery at a time. The Drake equation is one of the most famous attempts to estimate the number of intelligent civilizations in our galaxy. Proposed by astronomer Frank Drake in 1961, it's a formula that considers factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life developing on those planets. At first glance, it seems straightforward: plug in the numbers, and you'll get an estimate of how many extraterrestrial civilizations might be out there. But here's the paradox: even with conservative estimates, the equation suggests there should be dozens, if not hundreds, of intelligent civilizations in our galaxy. So, where are they? This question, often called the Fermi Paradox, highlights the disconnect between the Drake equation's predictions and our lack of evidence for alien life. One possibility is that we're simply not looking in the right way. Maybe extraterrestrial civilizations communicate using methods we haven't discovered yet, or they're so advanced that they've found ways to remain hidden. Another theory suggests that intelligent life might be incredibly rare, with civilizations self-destructing or failing to develop the technology needed for interstellar communication before they can make contact. Some even propose that we might be alone, a sobering thought that challenges our assumptions about the universe's habitability. The Drake equation paradox doesn't just raise questions about the existence of extraterrestrial life, it forces us to confront the limitations of our own knowledge. Are we missing something fundamental about the nature of life, or are we simply too early in our cosmic journey to find others? This paradox invites us to explore not just the stars, but also the deeper questions about our place in the universe. It's a reminder that the search for intelligent life isn't just about finding aliens. It's about understanding ourselves and the possibilities that lie beyond our world. Now, let's explore a paradox that challenges our assumptions about life in the universe, the Rare Earth Paradox. At first glance, the cosmos seems teeming with potential billions of galaxies, each with billions of stars and planets. It's easy to assume that Earth-like worlds must be common. But what if they're not? This paradox suggests that the conditions that make Earth so uniquely suited for life might be far rarer than we think. From our planet's just right distance from the Sun to its stable tectonic activity and protective magnetic field, Earth's habitability depends on a delicate balance of factors. Even something as seemingly minor as the Moon's presence, which stabilizes Earth's tilt and moderates its climate, plays a critical role. So, what does this mean for the search for extraterrestrial life? If Earth-like planets are indeed rare, it could imply that intelligent life is a cosmic anomaly, a fluke in an otherwise lifeless universe. On the other hand, it might mean that life thrives under conditions we haven't yet imagined, defying our Earth-centric assumptions. Some scientists argue that extremophiles organisms that survive in Earth's harshest environments prove life is more adaptable than we give it credit for. Others point to the possibility of life arising in completely alien ecosystems, like the methane lakes of Titan or the subsurface oceans of Europa. The rare Earth paradox doesn't just challenge our search for extraterrestrial life, it invites us to rethink the nature of habitability itself. Are Earth-like planets the only cradles for life, or are we limiting our imagination by focusing solely on what we know? This paradox reminds us that the universe is full of surprises, and the answers we seek might lie beyond the boundaries of our current understanding. It's a humbling yet exhilarating thought. In a cosmos so vast, the story of life might be far more unique or far more diverse than we ever imagined. Let's step into a hauntingly eerie scenario, the zombie universe paradox. Imagine a cosmos where the vast majority of stars, planets, and galaxies are lifeless, a universe that's mostly dead. While Earth teems with life, the rest of the universe might be a silent, barren expanse. This idea isn't just a dark thought experiment. It's a possibility that challenges our assumptions about life's place in the cosmos. On one hand, the sheer scale of the universe, with its trillions of stars and countless planets, suggests that life should be everywhere. Yet, so far, we've found no definitive evidence of extraterrestrial life. Could it be that most of the universe is a cosmic graveyard? One explanation is that the conditions for life are far more specific than we realize. Earth's habitability depends on a delicate balance of factors, from its stable orbit and protective atmosphere to its liquid water and active geology. If even one of these elements were missing, life as we know it might not exist. Another angle suggests that life could be fleeting, arising only to disappear before it has a chance to spread or evolve into intelligent civilizations. Perhaps self-destruction, cosmic disasters, or the harshness of space itself make life an incredibly rare and fragile phenomenon. But the zombie universe paradox also invites us to think differently. What if life isn't limited to Earth-like conditions? Could it thrive in environments we've never imagined, like the frozen oceans of Europa or the methane seas of Titan? Or maybe life exists in forms so alien that we wouldn't even recognize it. This paradox doesn't just question the existence of extraterrestrial life, it forces us to confront our understanding of what life is and where it can flourish. It's a humbling reminder that the universe might be far stranger and lonelier than we've ever thought, challenging us to rethink our place in the grand tapestry of existence. Now, let's unravel one of the most profound mysteries in science, the cosmic coincidence paradox. Picture this: the universe is governed by a set of fundamental constants, numbers like the speed of light, the strength of gravity, and the mass of particles. These constants are the building blocks of reality, shaping everything from the structure of atoms to the expansion of galaxies. But here's the twist: if any of these constants were even slightly different, life as we know it wouldn't exist. For example, if gravity were a fraction stronger, stars would burn out too quickly. If it were weaker, galaxies might never have formed. It's as if the universe was fine-tuned for life, a cosmic coincidence that defies explanation. So, how do we make sense of this? One possibility is that we're just incredibly lucky. that in a vast multiverse filled with countless universes, each with different constants, we happen to live in the one where the numbers align perfectly. This idea, known as the anthropic principle, suggests that our very existence biases our observations. If the constants weren't just right, we wouldn't be here to ponder them. But this explanation raises its own questions. Why does the multiverse exist, and why does it produce universes with such a wide range of properties? Some theories propose that the constants aren't arbitrary but are determined by deeper yet undiscovered laws of physics. Others suggest that our understanding of these constants is incomplete, and what we perceive as fine-tuning might be the result of underlying symmetries or principles we haven't yet uncovered. The cosmic coincidence paradox doesn't just challenge our understanding of physics, it forces us to confront the very nature of existence. Are we the product of chance, or is there something deeper at play? It's a question that invites us to explore the mysteries of the cosmos, reminding us that the universe is full of surprises waiting to be uncovered. Whether we're the result of a cosmic roll of the dice or part of a grander design, one thing is certain: the universe holds secrets that continue to inspire and confound us in equal measure. Let's dive into one of the most mind-bending ideas in modern physics, the holographic principle paradox. Imagine this: what if the entire universe, with its vast galaxies, swirling stars, and intricate particles, is actually a projection of information encoded on a two-dimensional surface? It sounds like something straight out of science fiction, but this concept is rooted in serious theoretical physics. The holographic principle suggests that all the information about our three-dimensional universe could be stored on a boundary, much like a hologram encodes a 3D image on a flat surface. This idea emerged from work on black hole thermodynamics, where physicists discovered that the information about everything that falls into a black hole is somehow stored on its event horizon, a two-dimensional surface. But what does this mean for our understanding of space and time? If the universe is fundamentally two-dimensional, then our perception of three-dimensional space might be an illusion, a kind of cosmic trick of the light. This paradox challenges the very nature of reality itself. Are we living in a world where depth and volume are just elaborate projections? Some theories suggest that the holographic principle could help unify quantum mechanics and gravity, two fundamental forces that have long resisted reconciliation. By treating space as a projection of information, physicists hope to find a deeper, more elegant framework that explains the cosmos. On the other hand, the idea raises profound philosophical questions. If the universe is a hologram, what does that say about the nature of existence? Are we, too, just patterns of information on a vast cosmic screen? While the holographic principle is still theoretical, it's a testament to the power of human curiosity and creativity. It pushes us to question the very fabric of reality, inviting us to see the universe in a way that's both humbling and awe-inspiring. Whether it's true or not, this paradox reminds us that the cosmos is full of mysteries waiting to be explored, and that even the wildest ideas can lead to groundbreaking discoveries. Now, let's tackle one of the most fundamental questions about the universe. Why does anything exist at all? This might sound like a philosophical musing, but it's rooted in a concrete scientific mystery, the Baryon Asymmetry Paradox. When the universe exploded into existence during the Big Bang, it should have created equal amounts of matter and antimatter. Matter, like the stuff that makes up stars, planets, and us, has a counterpart in antimatter which has the same mass but opposite charge. When matter and antimatter meet, they annihilate each other in a burst of energy. So, if the Big Bang produced equal amounts of both, why didn't everything just cancel out, leaving behind a universe of pure energy? The fact that we're here, surrounded by matter, means something tilted the balance in its favor. But what? One of the leading explanations comes from a set of conditions known as the Sakharov criteria, named after physicist Andrei Sakharov. These criteria suggest that the early universe must have violated certain symmetries like charge parity symmetry, which governs how particles behave. It's also possible that processes like CP violation, observed in certain particle decays, played a role in creating a slight excess of matter over antimatter. Over time, this tiny imbalance could have grown, leaving behind the matter-dominated universe we see today. But the question remains, why did these processes favor matter? This paradox isn't just a curiosity, it's a window into the origins of everything. If we can understand why matter dominates, we might unlock the secrets of the Big Bang itself. Some theories suggest that new particles or forces yet to be discovered could explain the asymmetry. Others propose that antimatter might exist in hidden regions of the cosmos, separated from us by vast distances. The Baryon asymmetry paradox challenges us to think deeply about the nature of existence, reminding us that even the most basic questions can lead to profound discoveries. It's a mystery that invites us to explore the universe with fresh eyes, eager to uncover the forces that shaped reality itself. Now, let's venture into a concept that's as unsettling as it is fascinating, the vacuum decay paradox. Imagine the universe as a vast, intricate structure resting on a precarious foundation, a so-called metastable vacuum. This doesn't mean your household vacuum cleaner. It's a term physicists use to describe the lowest energy state of space itself. Current theories suggest that the vacuum we exist in might not be the most stable possible configuration, but rather a temporary, fragile balance, like a marble sitting on the edge of a bowl. If something were to disturb this balance, say, a particle collision at extremely high energies, it could trigger a catastrophic event known as vacuum decay. Here's what makes this paradox so chilling. If vacuum decay occurs, it would create a bubble of true vacuum that expands at the speed of light, rewriting the fundamental laws of physics as it goes. Within this bubble, the constants that govern the universe, like the speed of light or the strength of gravity, could change, making life as we know it impossible. And the scary part, once it starts, there's no stopping it. It's like a cosmic domino effect that could reshape the entire cosmos in an instant. But here's where the paradox deepens. If vacuum decay is such a catastrophic possibility, why hasn't it happened yet? Some theories suggest that the probability of this event is astronomically low, making it unlikely in the lifetime of our universe. Others propose that vacuum decay might have already occurred in distant regions, but we wouldn't know because the bubble hasn't reached us yet. This paradox doesn't just challenge our understanding of the universe's stability, it forces us to confront the fragility of existence itself. It's a reminder that even the most fundamental aspects of reality could be subject to sudden, irreversible change. While the idea of vacuum decay might seem like the stuff of science fiction, it's rooted in the cutting edge of theoretical physics, pushing us to explore the boundaries of what we know and what we might never fully understand. Next, let's turn our attention to one of the most energetic mysteries in the cosmos, ultra-high-energy cosmic rays. These are particles, often protons or atomic nuclei, that hurtle through space at speeds approaching the speed of light, carrying energies millions of times greater than anything we can produce in particle accelerators on Earth. They're so powerful that when they collide with particles in Earth's atmosphere, they create showers of secondary particles that can be detected on the ground. But here's the paradox: scientists still don't know where these particles come from or how they're accelerated to such incredible energies. One of the biggest challenges in solving this mystery is understanding the mechanisms that could power these cosmic rays. Potential sources include extreme astrophysical objects like supermassive black holes, active galactic nuclei, or even gamma-ray bursts. Yet, even these powerful phenomena struggle to explain the sheer energy levels we've observed. What's more, because cosmic rays are charged particles, their paths are bent by magnetic fields as they travel through space, making it nearly impossible to trace them back to their origin. This means we're left with a cosmic detective story, piecing together clues from the particles that reach us, but the implications of this paradox go beyond astrophysics. Ultra-high-energy cosmic rays could help us test the limits of our understanding of particle physics. For example, they might reveal new interactions or particles that don't fit within the standard model, opening the door to entirely new theories of the universe. They could also shed light on the nature of space itself, offering insights into the cosmic magnetic fields that shape their journeys. This paradox doesn't just challenge our understanding of the universe's most energetic particles, it invites us to explore the boundaries of both astrophysics and particle physics. It's a reminder that even the most fundamental questions about the cosmos, like where particles come from and how they behave, can lead us to discoveries that reshape our understanding of reality. Whether we're searching for the origins of these cosmic rays or uncovering new physics in the process, this mystery pushes us to think bigger and explore deeper, proving that the universe always has more secrets to reveal. Now, let's turn our gaze to one of the most dazzling and perplexing objects in the cosmos, quasars. These celestial powerhouses are among the brightest things in the universe, outshining entire galaxies despite being no larger than our solar system. But here's the paradox: how can something so compact produce such staggering amounts of energy? At the heart of every quasar lies a supermassive black hole, millions or even billions of times more massive than our Sun. As matter spirals into the black hole, it forms a swirling disk of superheated gas and dust glowing with incredible brightness. This process, known as accretion, converts gravitational energy into radiation, lighting up the quasar like a cosmic beacon. But the energy output of quasars isn't just impressive, it's mind-boggling. A single quasar can emit thousands of times more energy than an entire galaxy, all from a region that's a tiny fraction of its size. This paradox challenges our understanding of how black holes work and how they interact with their surroundings. For instance, how do black holes manage to funnel so much matter so efficiently? And what role do magnetic fields play in shaping the accretion disk and channeling energy into jets that shoot out at nearly the speed of light? These questions aren't just about quasars, they're about the fundamental physics of black holes and the extreme environments they create. Quasars also offer a glimpse into the early universe. Because they're so bright, we can see them from billions of light years away, effectively looking back in time to an era when the cosmos was young and chaotic. This makes them invaluable tools for studying how galaxies formed and evolved. But their existence in the early universe raises another paradox. How did supermassive black holes grow so massive so quickly? Current theories struggle to explain how these giants could have formed in the relatively short time available after the Big Bang. This paradox doesn't just challenge our understanding of black holes and quasars, it forces us to rethink the nature of the early universe itself. Whether it's uncovering the mechanisms behind their immense energy output or unraveling the mysteries of their rapid formation, quasars remind us that the cosmos is full of wonders waiting to be explored. They're not just distant lights in the sky, they're keys to unlocking some of the universe's deepest secrets, inviting us to peer into the past and imagine the forces that shaped everything we see today. Now, let's journey back to a pivotal but puzzling chapter in the universe's history, the Reionization Era. About 400 million years after the Big Bang, the cosmos was a dark, murky place, filled with neutral hydrogen gas that absorbed light, leaving the universe opaque. But something happened, something dramatic. By the time the universe was about 1 billion years old, it had transformed into the transparent, ionized cosmos we see today. This process, known as reionization, is one of the most important and mysterious events in the universe's evolution. But here's the paradox: what caused it? One leading theory points to the first stars and galaxies. As these early structures formed, their intense ultraviolet light could have ionized the surrounding hydrogen, stripping electrons from atoms and clearing the cosmic fog. However, there's a problem. The number of stars and galaxies we've observed from this era doesn't seem sufficient to account for the scale of reionization. This raises a critical question. Were there more stars or galaxies than we've detected, or did something else contribute to this process? Some scientists suggest that black holes, particularly those in the centers of early galaxies, might have played a role. These black holes, feeding on surrounding matter, could have released vast amounts of energy, helping to ionize the universe. Others propose that exotic objects like population Roman 3 stars, the first generation of stars, made almost entirely of hydrogen and helium, could have been key players, though these stars have never been directly observed. Another layer of this paradox lies in the timing. Reionization didn't happen all at once. It unfolded over hundreds of millions of years, creating a patchwork of ionized and neutral regions. How did this process spread so effectively across the cosmos? Was it driven by the gradual growth of galaxies, or did something accelerate it, like cosmic winds or feedback from supernova? These questions aren't just about reionization. They're about understanding the universe's adolescence, a time when the first structures were forming, setting the stage for everything that came after. The reionization paradox doesn't just challenge our understanding of the early universe. It invites us to explore the forces that shape the cosmos we see today. It's a reminder that even the most fundamental transitions in the universe's history are still shrouded in mystery, waiting for us to uncover the answers. Whether it's the first stars, the first black holes, or something entirely unexpected, this era holds the key to understanding how the universe became the vibrant, luminous place it is now, and how we came to be here to witness it. Now, let's step into a concept that stretches the boundaries of imagination: the brain-world paradox. Picture our universe not as a vast three-dimensional expanse, but as a brain, a membrane floating in a higher dimensional space. This idea, rooted in string theory, suggests that the cosmos we know might be just one layer in a much larger, multidimensional reality. Think of it like this: if our universe is a sheet of paper, there could be countless other sheets stacked together, each with its own laws of physics, stars, and perhaps even life. But what does this mean for the nature of reality? If we're living on a brain, it could explain some of the deepest mysteries in physics. For instance, gravity might seem weaker than the other fundamental forces because it leaks into the higher dimensions, while the other forces are confined to our brain. This could explain why gravity is so much weaker than electromagnetism or the strong nuclear force, a puzzle that has long baffled scientists. It also opens the door to the possibility of other brains existing just beyond our perception, each with its own unique properties. Could there be parallel universes just a millimeter away in a higher dimension, completely invisible to us? The brain-world paradox doesn't just challenge our understanding of space, it forces us to rethink the very fabric of existence. Are we limited to the dimensions we can see, or is there more to the cosmos than meets the eye? This idea might seem like science fiction, but it's grounded in rigorous mathematics and theoretical physics. It's a reminder that the universe might be far more complex and far stranger than we've ever imagined. Whether brains are real or just a fascinating hypothesis, they invite us to push the boundaries of what we know and explore the possibilities of a multidimensional reality. Next, let's dive into a concept that sounds like it's straight out of a futuristic sci-fi novel: zero-point energy. Imagine tapping into the boundless energy of empty space itself, not just a little but an infinite amount. It's an idea that has fascinated scientists and dreamers alike, promising a future of limitless power. But here's the catch: while the concept is tantalizing, it's also riddled with paradoxes and challenges that make it one of the most controversial topics in physics. Zero-point energy is the lowest possible energy that a quantum mechanical system can have, and it's not zero. Even in a perfect vacuum where you'd expect nothingness, quantum fluctuations create a seething, energetic froth. This energy is everywhere, filling the fabric of spacetime itself. theoretically, if we could harness even a fraction of it, we'd have access to an inexhaustible energy source. But the reality is far more complicated. For one, the energy density of the vacuum is astronomically high, so high that if it were directly observable, it would warp the universe beyond recognition. This discrepancy, known as the cosmological constant problem, is one of the biggest unsolved mysteries in physics, but the paradoxes don't stop there. Even if we could access zero-point energy, extracting it poses enormous challenges. According to quantum mechanics, the vacuum state is the ground state, the lowest energy level possible. Trying to extract energy from it would be like trying to draw water from an already empty glass. Worse, some theories suggest that any attempt to manipulate zero-point energy might destabilize the fabric of spacetime itself, with potentially catastrophic consequences. Despite these hurdles, the allure of zero-point energy continues to inspire researchers. Some propose that advanced civilizations might have already figured out how to harness it, while others argue that it's fundamentally impossible, a cosmic tease just out of reach. The zero-point energy paradox doesn't just challenge our understanding of physics, it forces us to confront the limits of what's possible. Whether it's a future energy source or a tantalizing illusion, it's a reminder that the universe always keeps some secrets just beyond our grasp, inviting us to explore, question, and imagine. As we come to the end of our journey through these 50 space paradoxes, one thing becomes abundantly clear. The universe is far stranger, more complex, and more awe-inspiring than we could ever imagine. Each paradox we've explored, from the mind-bending mysteries of black holes to the puzzling absence of extraterrestrial life, from the bizarre nature of quantum mechanics to the vast unknowns of dark energy and dark matter, challenges our understanding in profound ways. They remind us that the cosmos is not a static, predictable place, but a dynamic, ever-evolving tapestry of mysteries waiting to be unraveled. These paradoxes aren't just abstract ideas, they're invitations to explore, to question, and to wonder. They force us to confront the limits of our knowledge and inspire us to push beyond them. Whether it's the eerie silence of the Fermi Paradox, the cosmic dance of the arrow of time, or the tantalizing possibility of parallel universes, each paradox offers a glimpse into the deeper truths of existence. They remind us that the universe is not just something to observe, but something to engage with, to marvel at, and to ponder. So what's next? The journey doesn't end here. These paradoxes are not just problems to be solved, but doorways to new discoveries. They invite us to keep asking questions, to keep exploring, and to keep searching for answers. Who knows what we might uncover next? Perhaps the next great breakthrough in physics or astronomy is just around the corner, waiting for someone, maybe even you, to take that next step. Before we wrap up, we'd love to hear from you. Which of these paradoxes fascinates you the most? Do you have theories or thoughts about any of them? Share your ideas in the comments below. We're excited to continue this conversation with you. And if you enjoyed this journey through the cosmos, don't forget to hit that subscribe button and join us as we keep exploring the universe's greatest enigmas. The cosmos is calling, and there's so much more to discover. Together, let's keep unlocking the mysteries of the universe, one paradox at